The production analysis of the firm brings into focus the process of production and related costs of production. We must take inputs into consideration applied for production and resulting into output. There are different methods to produce a commodity. The firm has to identify the technical efficient production process for avoiding any wastage of resources. These technical efficient production process provides a choice for choosing the least cost process. Thus, the firm also attempts to produce the maximum level of output for a given set of inputs, avoiding whatever waste possible. In short run, some inputs of production are fixed and others are variable. These variable inputs can be extended or reduced on a given fixed inputs which are operated intensively to yield some increase in output, without allowing to change the scale of the firm and the structure of the industry. The term production function refers to a physical relationship between the firm's input of resources and firm's output of goods and services per unit of time, leaving prices aside. Firm's inputs can be classified as capital, labor, and land. Labor and capital can be combined in different proportions in a production process. The general form of production function can be expressed as Q is equal to Q, I1, I2, In, where Q is the quantity of output for a production unit and inputs are represented as I1, I2, In. In economic theory, very often labor, L, and capital K are taken as variable. Total product or the total physical product is the output that can be produced using various levels of inputs. It depicts the various amount of output can be produced using various amount of labor. Average product or average physical product is the total production divided by the number of variable input employed. In other words, it is production per unit of input. Average product of labor is equal to total product divided by total units of labor. Marginal product is a very important concept of production analysis. It is defined as the change in output resulting from a change in factor of production, keeping all other factors constant. Mathematically, the marginal product of each factor is the partial derivative of the production function with respect to the factor. In principle, marginal product of a factor may assume any value. It could be positive, zero, or negative. However, basic production theory concentrates only on efficient part of the production function, that is, on the range over which the marginal product is positive. Ranges of output over which marginal product is negative implies irrational behavior of the firm and are not considered by the theory of production. The decline in marginal productivity of labor in the figure shown here is the reflection of the law of diminishing returns. Law of diminishing returns is an empirical generalization or a physical law, not a proposition of economics. It postulates that as more units of a variable input are used with a fixed amount of other inputs, after a point, a smaller and smaller return will accrue to each additional unit of the variable unit. Thus, the marginal product of the variable input eventually declines. This occurs because each additional unit of the variable input has less and less of fixed inputs with which to work. It is to be noted that to observe the law of diminishing returns, at least one input must be held constant. Technology is also assumed to remain unchanged. Initially, the marginal product of labor rises, reaches its maximum point, and then declines. Law of diminishing marginal product is illustrated through the schedule shown here. Unlike the short run, where only one factor of production is variable, in long run, all factors of production become variable, and returns to scale begins to operate. There are three stages of production, namely increasing returns to scale, constant returns to scale, and decreasing returns to scale. Increasing returns to scale occurs when the percentage change in output is greater than the percentage change in inputs. Constant returns to scale takes place when the percentage change in output is equal to percentage change in input. And as the name suggests, decreasing return to scale occurs when percentage change in input is greater than the percentage change in output. The table shown here illustrates the return to scale. It is clearly evident that when we employ 80 and 120 units of capital, the percentage change in output is greater than the percentage change in input. Thus, at these stages, increasing returns to scale applies. When the units of capital are further increased to 160, the percentage change in input equals the percentage change in output. Thus, this stage is that of constant returns to scale. Now, if we increase the units of capital to 200, we see that the percentage change in output is less than the percentage change in input. Thus, at this stage, decreasing returns to scale operates. The marginal rate of technical substitution measures how one factor of production is substituted for another, while keeping the output constant. Suppose, in simple case, output Y depends upon capital K and labor L, so that Y is equal to F bracket KL. And the marginal rate of technical substitution of labor for capital K can be determined as delta K upon delta L. We know that delta K can be written as delta Y upon delta L, and delta L can be written as delta Y upon delta K. Thus, we can also write it as marginal productivity of L, that is, labor upon marginal productivity of K, that is capital. The marginal rate of technical substitution as a measure of the degree of substitutability of factors has a serious defect, since it depends on the units of measurements of the factors. A better measure of the ease of factor substitution is provided by elasticity of substitution. The elasticity of substitution is defined as the percentage change in capital labor ratio divided by the percentage change in the rate of technical substitution. It is a pure number independent of unit of measurements of K and L, since both the numerators and denominator are measured in the same unit. An isoquant curve is a graph of all possible combinations of input that results in the production of a given level of output. Isoquants are used to measure the influence of inputs on the level of production on output that can be achieved. Here, let us also discuss that the slope of an isoquant represents marginal rate of technical substitution between capital and labor. Along an isoquant, we represent different techniques of production. The point A represents a labor-intensive technique, compared to B, which indicates a capital-intensive technique. Either of these techniques may be employed to produce some output. The proportion of factors depend on the nature of technology employed. An automated plant is more capital intensive, while many mega projects are technology intensive. When inputs are perfect substitutes, we get straight downward falling isoquants. When inputs are imperfect substitutes, we get the usual isoquant curve as in the diagram. In case of perfect complementary inputs, we get L-shaped isoquants. When we move from single-factor production models to two-factor production models, we find that beyond ridge lines OA and OB, it is not advisable to produce, because either marginal productivity of labor or capital tends to be zero. Thus, the production must be undertaken within the zone countered by the ridge lines. Now let us discuss the characteristics of isoquants. As we've already seen, isoquants have a negative slope in their economic region. The negative slope shows the two inputs can be substituted in place of each other. It means that if an input is reduced, then other input must increase, so that the total output remains the same. Also, isoquants are convex to the origin. This implies that inputs are substitutable and there is diminishing marginal rate of technical substitution between the input in their economic region. One very important characteristic of isoquants is that they never intersect each other. This means that an output could be produced with smaller as well as large input combination. We have already discussed that slope of isoquants is equal to marginal rate of technical substitution. Again, a very important feature to understand is that the upper isoquant represents higher level of output. The logic lies in the fact that higher isoquants imply larger input combination, which generally produces higher output. A profit maximizing firm seeks to minimize its cost for a given output or to maximize its output for a given total cost. Isoquant tells that a given output can be produced with different input combination. Given the input prices, however, only one of the input combination meets the least cost criterion. To determine the optimal combination of input is to add information on the cost of these inputs. This cost information is introduced by a function called a production isocost. Assuming two factors of production, capital and labor, and their per unit price, W and R, respectively, the total expenditure on K and L input is C is equal to RK plus WL. For any given cost, the isocost line defines all combination of capital and labor inputs that can be purchased for C. If R increases, then the slope of the isocost line will decrease, and it will move towards the origin on vertical axis. It means now, with a given budget, at higher rate of capital, the firm can purchase less amount of capital with the budget. On the other hand, if W increases, then isocost line will become steeper and will move towards origin on horizontal axis.